In a Rankine cycle, the fluid entering the turbine is a saturated vapor, and when this fluid is expanding inside the turbine, a partial condensation occurs. All along the turbine, the fluid is a mixture between mostly vapor but also droplets of liquid. The presence of these two phases inside the turbine has two negative effects on the machine. The first one is that the isentropic efficiency of the turbine is decreasing a lot with the presence of this liquid phase. This is due to the fact that because the vapor and the liquid don't have the same density, they also don't have the same velocity profile inside the machine, and so we increase the irreversibilities inside the turbine. The second big problem is that the droplets that are impacting the blades of the turbine tend to erode the surface and decrease the life length of the turbine. This expansion inside the two-phase zone is causing problems to the machine. In order to improve the Rankine cycle and to decrease these effects of two-phase expansion, one way of doing is to superheat the vapor before the turbine inlet. And this Rankine cycle with the superheat of the vapor at the turbine inlet is usually called the Hirn cycle. In order to do that, the fluid that is going out of the vapor generator and to the stratification tank, some saturated vapor is extracted from this balloon and is going back to with the heat exchanger to the vapor generator in order to be superheated. So when all the vapor generator is just simplified like on this schematic with one single heat exchanger, then we can just consider that A is not anymore a saturated vapor at high pressure, but a superheated vapor at high pressure. So vapor that is at a higher temperature than the saturation temperature corresponding to its pressure. So to which temperature is it possible to go at the turbine inlet? In fact, this depends on two things. In some cases, when the vapor generator receives heat from combustion, what is usually fixing the maximal temperature that can be admitted to the turbine is the mechanical properties of the turbine and what it can stand as temperature. In that case, the maximum temperature would be usually around 550 degrees Celsius or even 600 degrees Celsius. That's the maximum temperature that the turbine can admit without damage. In some other cases, for example in nuclear power plants, the maximal temperature is more fixed by the secondary part of the vapor generator, because for the primary circuits of pressurized water nuclear power plants, this maximal temperature is around 330 degrees Celsius due to safety reasons with the core of the reactor, and because we need to have a temperature difference between both fluids, then the outlet maximum temperature we can have in nuclear power plants will be 280 degrees about for point A. So anyway, we have some parameters that will fix this maximal temperature that cannot be over which we cannot go. and here we will plot this new Hirn cycle in a CS diagram. So once again, temperature, specific entropy, the saturation line, the vapor zone, liquid zone, and two-phase zone. Point A at turbine inlet is still at high temperature, but this time it's not saturated, but it's superheated until the maximal temperature. So point A will be placed over there. Then we have the expansion through the turbine from point A to the lower pressure, and we can usually define point B, the outlet of the turbine, in two steps. First, we need to place the adiabatic reversible, so isentropic point B is. That will correspond to the low pressure but same specific entropy than point A, and then using the isentropic efficiency of the turbine, we can calculate the specific enthalpy of point B. That will be placed at a higher specific entropy, but still on this low pressure isobaric line. And so like this we can plot schematically the transformation between A and B. Then from B, oops, that's not written the right way. From B to C, we have condensation of the fluid in the condenser, and that's here we consider, like before, C as being low pressure saturated liquid, and so we have this condensation. From C to D, the pump is increasing the pressure but not changing the other things, so we are going from the low pressure isobaric line to the high pressure, and then from D to A. In the vapor generator, the working fluid is undergoing three successive transformations. First, it's heated, and so until the temperature reaches the saturation temperature corresponding to the high pressure. Then the fluid is fully evaporated, and then the vapor is superheated until being again at point A. So that's the Hirn cycle. We can still notice one thing is that the problem we wanted to solve, having only vapor inside the turbine is only partly solved, because usually the outlet of the turbine, if we have a simple Hirn cycle, is still two-phase. So here it was very schematically, but maybe the isobaric line would be a bit more vertical, and we would have still one good half of the expansion inside the two-phase zone in such a cycle. So the problem is only partly solved with the Hirn cycle.